Good morning, everybody. My name is Kishor. I'm an engineer from Snap. Today, I'm talking about tweaking Valkey for high-rated workloads. And yeah, so for the past 1 year, I'm leading the efforts for migrating our 350 KeyDB clusters to Valkey clusters. And we are from a small team, and huge credits to all of the team. What you see here is all from them, so real credit to all of them. So we'll keep it simple today. Real numbers, real incidents, real fixes. All right. So as I said, when we are migrating all these 350 plus clusters from KeyDB to Valkey, we do have our fair set of challenges. And today I'm going to talk about like one specific workload, high write rate, high memory utilization, and the one failure path or one failure case dominates this workload, which is full sync loop. So before I delve into full sync loops, how many of you like got paged in the midnight, like 3 a.m. related to a full sync incident here? So I see quite a few hands here. Yeah, this talk is like relevant for all the folks who didn't raise your hand. This is how you keep it that way. Yeah. So since most of you is familiar with full sync loop, here is just quick refresher of how full sync works. Replica connects to primary, and primary decides to do a full sync, and then primary starts saving the RDB over the disk, and RDB transmits over the network, and then a replica starts loading the RDB, and then after that it starts replaying all the writes, and then it will be completed. At any point of time, if the replication buffer accumulated, the writes are accumulated in the replication buffer of the primary. When at any point of time the replication buffer gets full, this process like repeats. This is called like full sync loop. And speaking of that, just reminds me of my memory where I first joined this caching and storage infra team. I got paged in the midnight, and I see the replica restarted 43 times or maybe 46 times. Honestly, I lost track the count, and to the point that I questioned like what did I get into. Then that's when I realized we have actually a bigger problem. And when we actually like delve into that, this particular use case basically is like pretty interesting. When we basically think of full sync loops, we usually think about like high memory and high write rate applications. However, for very read heavy applications, like we get into that because like for us, like we had a bug where replica replica is in the full sync process. It hasn't loaded the cache yet, and app is sending the traffic to replica, and replica is responding the traffic with cache misses, and those cache misses are again backfilled from app to primary, and that is filling the replication buffer of the primary, and the loop starts, and it's also like making the full sync longer. And so when we did the audit of all the full sync related incidents over the 12 months across our KDB clusters, these are the root causes in the order of the frequency. The first being the replica not rejecting the traffic during preloading is the most common use case. And after that, the underlying write pattern could change. That could basically that could fill the buffer faster, or even the buffer was never right sized from the beginning, or like node failures cascading to full sync issues, as well as we also like switched to we were also using disk-based replication buffer at some point in KeyDB. Like when we were switching from in-memory to disk-based replication buffer, like we also had some bugs for that. So what we did in order to address these full sync issues, like we did mainly 3 actions. The first phase, I would say we are in denial phase. We keep chasing the write buffer size we keep tuning the write buffer size for clusters as we goes, and sometimes even as I said, we switched to disk-based replication buffer, and dynamically we were switching from in-memory to disk-based replication buffer. Well, it bought some time, but it didn't fix the underlying loops. Then we also worked on shortening the duration of the full sync by relying on forkless sync, as well as we also fixed that replication, the replica rejecting the replica taking the traffic in the full sync bug as well. And the thing that actually like adds the most value is applying the back pressure. So even before what it means is we implemented write throttling. What it means is we slow down the writes even before the buffer gets full. So takeaway is like back pressure like beats the bigger buffer size here. So that's how we built in KeyDB, but when we decided to migrate from KeyDB to Valkey, some of the features that we built at KeyDB are not available in Valkey. So, and however, for our migration, we didn't basically like migrate, port all the features that we built from KeyDB to Valkey. There is like one particular thing that we actually ported out to our internal fork, which we're planning to also port it to open source community as well. That is write throttling. We picked our write throttling, and there is something else that is not present in KeyDB that is available in Valkey, which helped our use case, which is the dual channel replication. So the combo of both write throttling and dual channel replication give us 3x more headspace than what we have at KeyDB, and here is the math that how it works. So before we have the write throttling and we only have replication buffer from the primary. When we enable the dual channel replication in Valkey, the little bit background here is like in the next slot also like we are going to see like how using fork needs basically 2x the memory in data. So for our use case, like we use 60% of the data memory just for the Valkey, and remaining 40% either for replication buffer or for fork or for the OS. Since we have the dual channel replication and replica doesn't need copy on write memory, so we instantly 2x the replication buffer size, and then we added the write throttling and the primary at 50%. So that gave us basically 3x the headroom, 3x the baseline of our replication buffer for all of our clusters. And then how it helped us for our migration is we actually did a benchmarking by taking the 100% utilization on the memory, on the highest possible memory for us with a 100% write rate. And from our benchmarking, it took us like 7 to 10 minutes for our full sync to be completed. We had 50% headroom for that, so we came up with the 15-minute threshold. And then we computed the time to fill buffer for every cluster for us, which is basically take the replication buffer size divided by the write bandwidth rate. So any cluster that is more than 15 minutes, it's safe to migrate. Any cluster that has less than 15 minutes, we either tune the replication buffer or we resize the cluster. So that's how we came up with, we were able to roll 95% of our clusters safely. And next up, like we are looking for forkless from the community. As we know, like copy on write can double the memory, and it also like could stall the event loop as well. Plus, from our own KeyDB, like from our production clusters, we know that forkless actually works. So, all right, yeah, that's all from my side. Any questions?